Welcome everybody to Integrability Journal Club. And today I'm going to introduce Oleksandr Gamayun from Amsterdam University, who will tell us about modeling finite entropy states with free fermions. Please, Oleksandr.
All right. Thank you very much for inviting, and good afternoon, everybody. So today I will tell you about some recent work this was published last December. And also I mentioned some work in progress that I do basically with two groups of people, with Kolya Georgiev and Yuri Zhuravlev in Kyiv, and Daniel Chernovitz and Jean-Sebastian Coe in Amsterdam. All right. So basically, the questions that we would like to study is correlation functions at finite temperature, or more generally, finite entropy states. So roughly speaking, it looks like this. So you want to calculate some two-point function of some observable O. And let's say you want to do it in an integrable model. So you know how all eigenstates looks like. Then you insert the resolution of unity inside. Then potentially you know all form factors, all the matrix elements, you know the spectrum. And now the trick is how to perform the summation of all solutions of beta equations. So there are two ways to approach this problem. So one is purely numerical. So basically there are some smart algorithms how to scan the Hilbert space and to choose the most relevant vectors, and it's called by name of Abacus. Or you can, if you really want to know the answer, you can go to the field theory limit, namely large X and large T, and then basically you can describe your system in terms of some boson field phi. And how you do it technically? Well, you just linearize the spectrum around some usually Fermi velocity. Then you present your observable as some polynomial of field, like vertex operators, etc. And then you compute these correlation functions in simple, well, free Gauss field theory. And I'll try to tell you how it also goes from microscopic point of view in this talk. And here usually people show this remarkable picture. So this is experimental data for the basically so this is what's it? Yeah, it's some so density structure factor. So basically Fourier of this operator, where instead of O it's some Z component of spin, I guess. And yeah, here is the result of experiments, and here is a result of implementation of this program of the Abacus. And if you zoom into the edges of the excitation spectrum, then you will get some predictions, some threshold behaviors that you will get from the field theory predictions. Okay, so this all looks very nice. However, the problem is that both these approaches fail at finite temperature. So the first approach, numerical, fails because, well, in fact, all form factors, they become very small, and to saturate some rules, you have to take into account exponentially many states. So because your states get some entropy that is like scales with system size. And basically the field theory approach, it fails just because the assumption of the linearity of the spectrum that is valid at all energies, of course, now it's not, it's not satisfied that good. So in this talk, I will try to study some basic toy models, however, which will allow me to account for this type of behaviors. So that's basically my motivation. And here is the outline of my talk. So first, I introduce.
Sorry, the picture doesn't change even though it's harder to compute. Or...
Yeah, because there are no picture at some reasonable temperatures. So yeah.
So there's no picture.
Yeah.
It wasn't measured.
Yeah. Mm-hmm. But I'll show you picture like okay. Yeah. Anyway. Right. So basically, this is the outline of my talk. So first, I will introduce an object for whom I want to study this finite entropy or finite temperature properties, and this will be some just Fredholm determinants. And first, I will consider what I will call continuum system, which will be connected with sine-kernel. So, and I'll just go step by step. So I'll tell how this field theory that I just outlined works from the microscopic point of view. And then I'll address basically what to do at finite temperature. And this will be like first part of my talk. Then after the break, I'll tell how to deal with systems in the lattice. And there will be a lot of new phenomena. And mainly I will talk about static correlation functions. Well, because as I just explained to you, the main problem is that you have some very weird combinatorics of excited states. And then I said, I thought, yeah, just having 0t, it will be enough. But in the end, if I have time, I'll show some work in progress, what changes if you also include time. All right, so let's get started. So main hero of this talk will be Fredholm determinants of integrable kernels. So roughly speaking, this object, which I will also call tau functions. So what is written here, it's Fredholm determinant of the operator V that acts on some contour gamma, and the kernel, and the operator, its action is specified by the kernel, which is just a smooth function of two variables, and just kernel acts just by the convolution. And I have to say that the object defined in this way, it's a very natural generalization of just normal, let's say, Riemann integral. So if in Riemann integral you have some quadrature, so some weights and some points, when you split the integral and when you compute the sum, you'll get an integral. Similar you can do for Fredholm determinant. Simply you can consider it as a limit of this form. So you have the kernel evaluated at the points of your quadratures with the corresponding weights, and then the limit of this object as the size of matrix increases, then you will get basically what is called Fredholm determinant. So this is a constructive definition. Of course, there are many other definitions, and but the point to emphasize here, so the Fredholm determinant is as good a special function as any other you can imagine. Just right. And in my talk, I will have different choices of the contour gamma. So it will be either part of real line for zero temperature, or the whole real line for finite temperature case. And in this case, yeah, I will introduce the factor which I will call Fermi distribution, or in the latest this contour gamma, it will be just this one. Okay, so even more specifically, the first hero, the hero of the first part of my talk will be this generalized sine-kernel. So here I just write well the kernel. So it's basically just a sine and some prefactor, which constant mu, and this function in f that normally would correspond to the this function will regulate either you have zero temperature case or finite temperature case. And this object, it appears in many places. So the most natural probably it appears in random matrices when you compute the emptiness formation probability. Also, it comes naturally from impenetrable bosons, from mobile impurity systems. And in these two cases, this NF really plays a role of Fermi weight. But in more specific problems, like Schmidt echo on the domain wall in XX, then you see this NF is just some exponential factor.
Can I make a short remark?
Yeah, sure.
Don't you think you have a typo? There is maybe 2 x's below in the subindex of the Hamiltonian exponent. 2 x's, not 3, right?
No, 3. So
all 3?
Yes.
This is not 3 fermions.
This is not 3 fermions, yeah.
Okay.
Yeah, that's yeah. So yeah, the way it was solved, it's okay. So the comment here is the reason why you managed to get an explicit answer is because of this specific state. So somehow you can, and specific observable. So somehow you can connect this return probability with the partition function of the 6-vertex model with like very specific boundary condition, which you can somehow evaluate by. But,
this domain wall boundary condition by any chance? Domain wall boundary conditions?
Yeah, exactly, yeah. But it's not my work. It's just the demonstration that this function in F can be any. So for instance, in the other problem, that's again this was persistence of some spin configuration also in other. This in F play just one of the cos Q.
So what is P and Q? Oh, what is P and Q?
Okay, so here, right. So I specify my operator by its kernel, and kernel depends on here it's Q and Q prime, but in the next slide it's Q and P. Right?
All right, thanks.
Okay, so
and the x is just parameter.
X is just a parameter, yeah. So it depends, and nu is
Then
also parameter.
this tau and another tau, they have nothing to do with each other. Well, you have two taus.
Yeah, yes. Sorry about that. Yeah, but I just copied from the paper. Yeah. So yeah, you're right.
Sorry, just another simple question. What is the actual spin chain? What is its Hilbert space? And is it an infinite volume?
In which example?
Well, in this example, so when this kernel acts on something,
I believe, yeah.
So this means it acts on the Hilbert space, or how is it?
So I think you take. Are you worried that it's not periodic?
No. I'm just trying the basic questions. On the previous slide, you introduced some operators with some integration kernel. So how does it relate to the spin chain? You have XXX spin chain, and then what is the Hilbert space? Is it some infinite dimensional representation of?
So there are many physical problems where these types of objects appear. So one of them is random matrices. One of them is impenetrable bosons, and sometimes they appear in spin chains.
Okay, thanks.
Right, and also they.
But still, sorry, but still, it is probably large limit. Yes.
Yeah. All interdynamic limit. Yeah.
Yes.
Yeah. All system sizes are taken to infinity. Well, otherwise you cannot. Okay. And last example, which is I think very nice, but it's really work in progress, is when you consider classical integrable systems, and then you do inverse scattering, and then the role of this NF it's played by the reflection coefficient, and then to find asymptotics of the field configuration, then you also have to evaluate objects like this. So what I'm trying to say with this slide is that this is ubiquitous, and we'd like to find the large X asymptotics of this object that is a function of X of contour and a function of some function NF. So this would be my goal. All right. So
can you give some simple physical explanation why thermal states is encoded in this way? So why you put just here in this place?
Yeah. So okay. There is another presentation for the Fredholm determinant, which you treat determinant as a series in traces. And then basically when you consider trace, then you sum over all possible states with excitations, and then NF is just measure its density, basically. Well, it's I don't know whether it's a good explanation or not, but
the traces, it is just multiple integrals of this.
Yeah, and all these multiple integrals, NF of Q will come into the measure. So somehow it's responsible for the density of the excitations.
Okay.
Right. Okay. So yeah, and this I will call continuum because basically this Q and P they run through the real line, and my second example will be basically also generalized sine-kernel, but on a lattice. So what will be the difference? So two differences. So first there will be some finite rank present, and the second difference will be that instead of P minus Q in the denominator, I will have sine P minus Q, and they will live on S1. So they will run from minus pi to pi, and this particular tau function, it comes from the XY model. So basically, what is it? It's the spin chain. The spin chain with anisotropy gamma and the external magnetic field H. And this tau of X is nothing but just sigma X correlation function, finite temperature. Right. And yeah. And in this case, instead of an F, we have this function. So you see, it's kind of similar to Fermi distribution, but it also depends on the parameters of the model and yeah, and basically on the state. So this model, it can be solved by the appropriate first Jordan-Wigner rotation and then Bogoliubov rotations, and then you will have fermions with such spectrum, and yeah, and the Bogoliubov angle that you need, it can be expressed through the parameters of the system H and gamma like this. And then all this theta and E, it just comes into this single function. So in this sense, it's just, well, natural generalization of this model. But this is going to be after the break. Okay, so let's get started first with sine-kernel in the most simple setup. So we have zero temperature. So our determinant text on a segment from minus kf to kf.
But sorry, can I ask some question just to keep some logic in mind? So about previous slide. So in practice, how it works? So you start with this Hamiltonian, for example, yes, and you have some large but finite L. Mm-hmm. So then you solve it, and everything is discrete. Yes, everything is discrete and quantized. Yes.
Yes, but then you send L.
Then you formally calculate this two-point correlation function tau, mm-hmm. and then you should, in the limit of large L, rewrite it as this Fredholm determinants.
Yeah, exactly, and that suits very well the definition of Fredholm.
So and it is done more or less right by definition. You really write the infinite sum of this Fredholm determinant as multiple integrals and show that it matches this expression.
Yes, exactly, and it's very natural because then indeed you will have some determinant n by n, and then it will have 1 over n in front, and then as in this form it will be very easy to take limit. But it's not my work, right? I already take known answers and I'm trying to reinterpret it. Mm-hmm. So in particular, but very good. This question is very indeed there is.
Alexander, can I make a comment in here? Yeah. Or on the previous question? There is a textbook about this. Can I give a reference to this textbook? Maybe I just send this through chat. You can
right. Yes, send to everyone.
I send the reference through the chat because I mean there is a lot of questions about how it works.
Yeah. I suggest so I get so as for me. But I don't insist. Right. Okay. So yes, and now the idea is exactly as was mentioned. Okay, let's try to find some. Let's try to model the system with some free fermionic system, such that in continuum limit it will reproduce the same Fredholm determinants, but on the form factor series we will be able to find some asymptotics, and this way we'll find asymptotics to the whole expression. So that's the whole idea. So in particular for this model, how does it work? Well, we just postulate that this determinant can be obtained as a summation of the following form factors. So you have systems of n fermions, and n, yeah, it will, and kf, okay, and kf will be something like pi n over L. So when I will send n to infinity and L to infinity, I want just this expression to be constant. Okay, so then you have n unshifted just three fermions, which you just specify by quantum numbers n, and they quantize normally, and another set of the shifted fermions, and the phase shift is exactly coded by this nu, which will appear here. And then you'll just specify momentum. Okay, energy now we don't consider, we consider just static. And then as a form of overlap, I'll just postulate this simple formula, which is just a Cauchy determinant and with some prefactor. So sometimes I call it form factor, sometimes overlap. It's basically the same. And then the claim is that if you, this is very simple sum. And the claim is that you can just sum it completely over K. You just consider, you just reinterpret this product of determinants as a product of two matrices, and this, in the sum you just use Cauchy Binet formula, and then you will get some determinant. And the claim is that exactly in L to infinity and N to infinity limit, you will get this form. So, okay, so this is a claim.
Yeah.
And the proof is simple, so I'm not giving it here.
Can I ask a very simple question? So it is free fermions, and quantization for Q is clear. Yes, it looks periodic boundary condition. So, but K, you have sum over K, so it is a decomposition of unity. Yes. So yes. Why quantization for K is different from Q? So
well, you can consider this O as if it's introduced the shift. So O can be like a twist operator, for instance. But again, we just try to model the system.
Sorry, O is O. So you have a matrix element of operator O between two states, Q and K. So O.
I mean, theoretically, O can change boundary condition. What he's saying that operator O change boundary condition from periodic to twisted and new is twist. That's what he's saying.
Yes. Either this, or you can just look indeed on O as a definition of this guy. Then nu will be explicitly written here. And then it will be again just sum of the integers that will not change much, right?
And what is this operator? So it is some particular operator.
Yeah. So this operator was chosen exactly such that after you perform this summation, you will get this. So originally you could get this like from I don't know, from random matrices consideration from something else.
But in terms of free fermions, how does it look? In terms of free fermions,
this operator.
Yes.
Alexander, can I insert one quick comment? For example, if I take impenetrable Bose-Gas or just Luttinger Bose-Gas, I can consider excitation spectrum, and then out of multiplicity of all the energy levels, one can derive elementary excitation, and this elementary excitation actually has topological charge, so it does not fit into periodic boundary condition. One required to change periodic to anti-periodic. So twisted boundary conditions all over the place. It's very natural to consider.
Right.
Sorry for
but in
interruption.
Luttinger, this shift could be just 1/2, and I wanted to be like free variable.
Very good idea. Very good idea.
So and later it will be promoted even to arbitrary function.
Yes, of course.
So that's the whole idea. But just to it usually looks unnatural, but indeed this O, roughly speaking, it's something like a Jordan-Wigner string. Just X and then I nu and then integral C dagger C. So normally when it's pi, it changes exactly just 1/2, but here it's just some particular. But operator, sorry, but operator realization is not important. I just declare its matrix elements, and when you have a matrix.
Just one comment. So these operators are very, very natural, and that's operator change statistics from bosonic to anionic, actually, when you have arbitrary parameters.
Yes.
I apologize for interruption.
No, it's great comment. Thanks. Okay, all right. So this was like key point. So I'm glad there are a lot of questions. All right. And then basically what will be our procedure. So far, I just showed you this step. Okay, I'll declare it. So we have some operators, we perform summation, and we get this. Now, how to extract large extents asymptotics from this series? And the procedure basically goes as follows. So first, out of all states K, you identify some that you will call basically, vacuum state. In this case, it's very easy. It will have the same quantum numbers as a state Q. Then you consider basically the scaling of this overlap, and it turns out to decay with the system size with some power. And that's usually called orthogonality catastrophe. Then, so basically there is no one single state, and then you have to perform summation of some infrared modes, so soft modes, to satisfy the sum rule. So get something that at least will be finite at the large system size. And here and how to perform the summation. That's how Bosnianization comes to help, because it turns out that the form of this form factors of this Cauchy determinants, when the excitations are soft, and soft means they differ very little from this vacuum. They just identical to the matrix elements of just bosonic fields in the fermionic basis, where the excitations on top of the vacuum can be identified excitation of the Dirac vacuum. And then the summation is basically pretty simple. So you just it just reduces to the resolution of unity. Then this correlator in the in the Gauss just simple power. And what is a kind of advantage compared to traditional Bosnianization, that you get this prefactor, because you know it from here, and also some oscillation which measure like difference of the, well, in this case, momenta between well, Q states and vacuum state. So that's basically.
Sorry, so you linearize around this Fermi vacuum? Is that what's going on?
Yeah, so I'm saying that so out of all this K, I choose some, and then I consider excitation on top of it. So schematically it's shown here. So I just take into account only these excitations. And then
the main spectrum by like a free spectrum, essentially. Right?
Yeah, but here you see here it's not spectrum is not that important here. In this picture, it's important that these form factors, they will have much simpler form. I mean, I have some extra slides, so maybe if we will have some time, I can go through details, because it's really beautiful how it happens. But that's basically the idea of Luttinger liquid, well, in a nutshell. And it's not my idea; it's many people contributed to it. So I tried to list somebody, but of course I forgot somebody. So I apologize in advance. Okay, but let's see how this operation works for the most simple case when nu is constant. And okay, so when nu is constant and we choose the same integers, just consecutive integers for q and k, then we have to evaluate this Cauchy determinant, which is double product, or the standard, and then we can do it actually exactly. So here is the evaluation. And right, so here is the exact answer. So we have a double product, which gives us gamma function, and so single product gives us over integers give us gamma functions or ratio of gamma functions, and the another product gives us ratio of Barnes functions. So g of x, it's basically Barnes g functions that's just specified by this property, and compare with normal gamma function. Yeah, so but it's very well tabulated function. So yeah. Okay, so this is basically our overlap, and sending n to infinity, we get prescribed orthogonality of orthogonality catastrophe. So some prefactor and some power law. Right. So we did it for constant nu, but if nu would be a function, this computation wouldn't change much. Yes, there will be some integral, and instead of nu here, we'll have values of nu at the boundaries of the Fermi C. But otherwise, it's like conceptually, it's the same. It's some prefactor and some power law. Okay, and then basically, then to find large x asymptotics of our problem. So what we have to do, we have to basically replace this n by this x and multiply by some exponent. So that's what we're gonna do. So that's basically so done. So tau of x is just exactly this Fredholm determinant, and this is asymptotic. And here's the comparison. So black dots are just numerical evaluation of the Fredholm, and this red line is just this function. So you see, it covers like everywhere except maybe 0, where tau of x is going to 1, and this just diverges. And moreover, it takes into account even more subtle effects. So in fact, you have to take into account all integer shifts over nu. So if you go into details, then you also see this. So that's how basically we find asymptotics at 0 temperature. So that's how Yeah. All right. So that's so now let's try to use this approach at finite temperature. Just
So this tau and the another tau are different.
no, this tau is literally this determinant 1 plus e to the pi I nu minus 1 over pi, and then sine x p minus q or
No,
p minus q.
before tau was something which was sitting inside determinant. No? Was it not?
Yes. Sorry, I couldn't hear you.
Previously, you
Can you
defined tau, which was parameter inside determinant. Is it,
Degeneration
no,
notation. There was degeneration notation.
yeah, but
No, look, tau is defined in this red box.
almost continuous spectrum of notations.
Right. There is also, in classical complete integral model, there is tau function. So that's the one actually.
Yeah. Tau is always tau function.
Well, but you have tau
That's
also
the
in some way in the exponent in the XXX Hamiltonian.
Okay, yeah, it's fine.
That was, I apologize for that. Yes, sorry. Okay, so
by the way, at that point, if it's noticed, so does it satisfy some bilinear equation like?
Exactly, it satisfies Toda equation. Moreover, this Toda equation can be written as pen level 5, and yeah. So no, it's a lot of known about this function. Yeah, it's some pen level 5, and that's basically it's asymptotic. So and this product of Barnes is just what is called connection constant. Because you have one solution that starts at 0 with 1 plus and then you have to find another solution that has power law divergence at infinity, and then this constant. So that's kind of nicely connects all.
And this is sum over news, where it comes from, where it has this?
Because here
like mod numbers, something like this.
Because here, if you just shift nu by some integer, it will not change the value of the determinant. However, when you like limited yourself to the to this guy, then your nu is more or less fixed, and this shift of nu it's described another very specific low energy excitation, which when you take one particle from here and move it all the way here, and that's gives your nu shifted by 1. But normally, because of this structure, shifting nu by 1, it will gives like subleading corrections. So usually you don't care about this.
Subleading in 1 over.
Yeah, because x is supposed to be large.
X supposed to 1 over.
And, yeah. Okay, good. Right. Okay, now let's see what briefly we can do about finite temperature. So as I promised, finite temperature will be the same expression, but with some function here. However, this summation approach now no longer works, because now instead of power law decay, you have some exponential decay, and the number of soft modes, it also increases like dramatically. And it's very difficult to keep bookkeeping of this excitation. At least we could not. So what we're supposed to do is to use some heuristic approach instead. Namely, we would like to map the systems back to 0 temperature, at least in terms of excitations and combinatorics of excitations, such that to keep this kernel. So that's where this nu that depends on k comes into play. So here, basically, we just declare this to be, just nu that depends on t. And of course, it's very easily to solve this equation, and it's just this. And then basically you just substitute it into formulas for 0 temperature, and then you get this. So again, this.
But how come like you have kind of fundamental difficulty in computing it directly, but then just by change variables it becomes simple? How come?
That's kind of achievement. That's exactly why I'm giving the seminar.
Can I make a comment?
Yes.
Well, maybe it's appropriate in the end. I mean, I still like this Hamiltonian with 2 axes instead of 3 axes, and which is isotropic version of your xy when xy gamma equal to 0. Yeah. Then this is xxx. In xxx, one can calculate those asymptotics, and then one similar approach works. And then one can calculate asymptotics, and one can write differential equation, which is Apolovitz-Ladik differential equation, famous discrete nonlinear Schrödinger, and one can calculate asymptotics. That's a link. Sorry, for the x-axis, two axes, two axes.
Mm-hmm.
Okay, so
right. So indeed. Okay. So to be completely honest, of course, this object and the asymptotics were studied before, and the normal approach for this is what is called Riemann-Hilbert problem, because
yes,
this kernel has a very specific structure. Well, you can consider this approach as like, how can we compute asymptotics of Fredholm determinants without solving Riemann-Hilbert problem?
Yeah, right.
But,
okay, I understand. Maybe I just also sent some reference, but please continue. Sorry for interruption. I apologize.
Right. So okay. So this is a formula, and again, I just emphasize it comes literally from the from this finite size analysis, if you want. Yeah, except this nu is now dressed by the state. So previously nu was just a parameter of the model. Now it also depends on the state in which you compute your system, and that's one. And second, you see, previously nu was the real parameter. Now, because of this dress, it gets some imaginary part, and because of this, and now this structure is not just oscillations, but it contains some decay. So that's how you got your correlation length. So now your correlation function, instead of being like just power law decay, it starts to get this exponential decay. And let's see how does it work. Yeah, so basically here for different values of temperature, again, blue dots, yeah, it's a little bit small, but blue dots are exact computations, and red is just this asymptotics, and you see that it works perfectly when x is more or less large. So, okay. Right, but normally, so last comment before break, normally the approach of the finite temperature to the field theory is as follows. Yeah, suppose you want to compute some observable at finite temperature, then you will just, yeah, and this is a gapless system. Then you will argue that it's described by the CFT, then you will do this transformations, and you will map basically on a cylinder. And then the CFT prediction, and that if you at zero temperature had power law, then you will have, well, basically singe, right? And then if it's true at more or less all temperatures, then you expect that your inverse correlation length will be just a linear function of t. But of course, we can just take this imaginary part of this guy, compute 1 over c, and here is the curve. Again, dots are exact answer, and curve is really asymptotics. And you see, well, it's linear with correct slope only at very low temperatures. Well, and that's where, well, this traditional field theory is really applicable only around this origin. All right. All right. Okay, so let's do a break now, and then I'll tell what's new in yeah, in latest. So shall I continue? Right.
Mm-hmm. Yeah, please.
Okay. So then. Okay. Okay. So then let's consider another system, and this time it will be really on lattice. Namely, it will be just XY model, as I promised, and here it will be it start at the beginning. It will start look like cheating, because now instead of one determinant, I will have two, but in the end, I will like compress it into one again. So, but so far this is my object of interest. So it's just again sine-kernel, but now instead of p minus u in the denominator, I have sine p minus u, and now I have only limited number of integers that I can excite, because it doesn't make any sense to shift p more than 2 pi. So we can assume that p and q, they both leave from minus pi to pi. Yeah, and yeah, in this particular scenario, this function, it contains both state information and model information, if you wish. Yeah, so then, yeah, we would like to find the large asymptotic of this guy, and the procedure will be the same. We would like to develop some effective, to model the system again with free fermions, even though it's okay. So here I propose.
Sorry, here you also did such something like is Jordan-Wigner transformation.
Well, yes. Well, not me. Let's say I just went to archive and just downloaded the answer.
Mm-hmm. Yeah.
So
I mean the spectrum for this fermionic.
Yeah. So this model, So in original fermions, it's pretty tricky. So they are Majorana, so they have excitations in pairs, and here is the spectrum. At zero temperature, you have a quantum phase transition. So when H goes at 1, so the gap is opening. So everything looks complicated in original fermions. But we would like to have like our own fermions, so some effective form factors. Such that, again, so procedure, such at one point we will just reproduce this guy exactly. And on the other hand, it will be much easier to sum when X is large.
Yeah. Could you do beta ansatz instead of these transformations?
Yeah, but beta ansatz, but well, you can solve exactly. I mean, but of course you can do beta ansatz, and then what? Like, beta ansatz gives you spectrum states, but then, as I said, it's the main difficulty comes from that you have to sum over all summations of the beta states.
I mean, can I add some philosophy? Beta ansatz solves the model. I mean, if you have an integrable Hamiltonian, you diagonalize it. But correlation functions, roughly speaking, this is linear response. So it describes what happens if I perturb Hamiltonian a little bit. So I actually go away from integrability. So correlation functions are much more complicated than eigenfunctions. That's my philosophy. Sorry for interruption.
So normally, like solving, exactly. So correlation functions, not only you have to solve, you have to find eigenstands, you have to know, form factors, but also the main like complication comes from all the sums that in principle over like infinite Hilbert space.
But I mean, we already know the answer is a determinant. Now the question is how to compute the asymptotics, right? So
But okay, and the speculation is that in the interacting system, okay, you don't have.
Oleksandr, let me. I have an old-fashioned philosophy which briefly was mentioned here. So our old-fashioned philosophy, which is in the book, which I transfer, was the following: okay, we got determinant. Okay, nice. What we do next? We try to write differential equation for this determinant. So sometimes possible in the x case, 2 x's, we managed Ablovislatic. Nice. What we do next? Ablovislatic is completely integral, classical. We try to solve it. It's Riemann-Hilbert. Sometimes we can push through in the xxx case. We manage to get asymptotic. But Oleksandr, probably my understanding that Oleksandr suggesting more efficient form, which is faster and cut to the answer faster, because always kind of really complicated 3 steps, monstrous procedure. Sorry for interruption.
Yeah, exactly. That's exactly the motivation. So okay, because indeed, most of this problem can be analyzed by Riemann-Hilbert, but
this is faster and more efficient.
And more kind of intuitive.
Of course,
okay, it has this like logical step. Why would you consider some effective fermions? But after that, it's pretty smooth. Okay, let's do what is declared. So here it will be a pretty similar double product, but now sines instead of just linear functions. And because we have this extra finite rank, the number of k's will be 1 plus 1, n plus 1, sorry, 1 more than number of q's, but otherwise it's same. And then again, q will have normal quantizations, and k will be quantized with a phase shift nu, which means that it's just solution of this equation. And then the claim is, I'm not proving it, but if you perform summation over q, you will get the tau function, where these kernels, they differ from the sine-kernels by something which is exponential in x, exponentially small in x. Okay, So this is a claim. Now,
but before it was exact, right? Now it's
before it was the same. Yeah, sorry. Yeah, no, it was also. No, sorry. Before it was exact. Yeah, yeah. Mm-hmm.
So it is the whole equation. It is two exponents. You just take log and obviously get solution. No.
Yeah. So yeah, that's what I'm saying. It's nothing complicated. So here, instead of this, I wrote just this, right? It's just solution here. It's just
Okay.
K 2 pi L n and nu n, just some phase shift. Nothing complicated so far. Just notations. Very good. Okay. Right. And right. So yeah. So then why we choose this new? Then we get this prefactor. So then if we neglect this exponential corrections, if we want to reproduce our problems that we want to solve, so xy, then we have to perform this identification between our effective nu and the parameters of the model, the Bogoliubov angle and the energy of excitations. Okay, and now comes something very peculiar to the lattice. It turns out that depending on the parameter, namely on the magnetic field and anisotropy, this nu, because it has this Bogoliubov angle, it might have some non-trivial winding number. So for instance, for H 0.7 and gamma 0.3, you have exactly winding number 1. So you're somewhere in this domain. If you're in this domain, so 1.1, yeah, and what is it? Yeah, 1.1 and 0.3. Then you have no winding number, and also you can have negative winding number if this gamma is negative. Right. Okay. So now let's proceed to our form factors summation, and now let's look at the of this form factor. And first, let's estimate their number. We'll start with case when delta is 1. So then, yeah.
So this delta, could you remind?
Delta is a winding number.
Oh.
So depending on the parameters of the model, this function can have various winding numbers, which we didn't have in continuum.
Yeah, I mean winding that when you go by 2 pi, it's
yeah. When you go from minus pi to pi, yeah. Sorry. So now you very good. Sorry. Now you have a Brillouin zone, which is S1, and you have this theta, which is also S1, and then one S1 can of course wind another S1 as many times as it like. Okay. Right. Okay, so let's have a look at the total number of solution. So for Q, it's always at most L solutions to stay in the Brillouin zone, but the number of solutions of this equation actually it different with different deltas, which was also new comparing to continuum. Well, you can argue that the number of solution is actually L plus delta. Well, the easiest way to see it is just extract winding part of the nu, then you will get to that it will effectively modify L, and the same as here you had L solutions, here you will have L plus delta. But also you can just write graphically and persuade yourself. Okay, and now another amazing thing happens. Imagine we consider exactly delta equal 1. So then number of solutions of case is exactly L plus 1, the maximal number. And since in this case, so number, because of this finite rank, the number of case are n plus 1 and this n, then we can choose this n equal to L. Then And then basically because of the Pauli principle, there will be exactly one way to pick L ordered numbers out of L positions. And that instead of the whole sum, we'll have literally one form factor. So that's kind of amazing. And then it turns out, well, that's the claim. And then the claim is that this tau function, it will be just this exponential, and that's it. So once again, what happened? Instead of considering true tau function, we just modified kernels just a little bit, just by some exponential. But it turns out that this tau function with slightly corrected kernels, it's just actually elementary function. So it's just some prefactor and x to some, and that's it. And then, of course, you argue, okay, then asymptotics to my original problem is just this. Well, okay, it's not really mathematically rigorous, but you kind of expect if kernels differ a little bit, then determinants also differ a little bit. But it's a subtle point because we know some counterexamples. Okay, and now let's look precisely at the asymptotic. Yeah, so it contains all this linear function and some double integral. And what's interesting in this double integral is that this nu, it's exactly such that with this correction, it's exactly such that it does not have any winding. Yeah. So this is the answer. Okay, now, but that's we got lucky because delta was 1. Now let's consider the different deltas. Okay, so for delta equals 0, again, the full number of solutions for Q is just the same. However, the maximal number of K is just L. So they fix somehow. And then because the number of Q should be one less, there will be, we'll have to create some hole in this. So then this sum over all 4 factors, it will be sum over all of this, if you wish, holes. Then instead of going to soft modes, actually we have to estimate like exactly in the middle of the spectrum. Then the sum transforms into an integral, which we compute and get similar answers. So it will be well, this answers that we had for delta equals 1. But now, because nu has 0 winding number, we don't have to subtract anything, and some prefactor, which is natural. Actually, we could use the same approach even for delta equal 1, because, okay, in previously we chose L and L plus 1 numbers, but in principle we could choose N and L minus 1. In the infinite L, it shouldn't matter. Then even for delta equal 1, we still would have the sum of L terms. However, in that case, only A equal 1 and the A equal N would matter, and then we would recover answer from the previous slide. Okay, so that's how does it work. And for any negative delta, then you'll just create N holes, and then your answer will transform into this nice form. So you will have this prefactor, which typical for any nu. Just you have to consider this shifted nu without winding number, and there will be some prefactor, which which has also this very specific form. And okay, in the case when nu is well, in the case when nu corresponds to the XY model, this was structure was somehow recovered for by McCoy and others. And in general, this structure comes from the mathematical works on Kepler's determinant, and hopefully I will comment on it later. But yeah, that's the whole procedure. Yeah, so basically, once again, probably I didn't say it properly. So even though here you might think that here you have to sum over, at least you will have n-fold integral of the position of these particles, but it turns out, because of this specific structure of form factors, in fact, everything factorizes only into one-dimensional integrals. Yes, that has to be emphasized. And then you have just to take this determinant to account for the number of excitations. Okay, so that's basically considers that basically finishes like arbitrary consideration for arbitrary nu. If we now return back to our original problem about XY model, then actually, so here I considered only delta 1 and delta 0, delta minus 1 is automatically. So delta 1, it's this ferromagnetic regime. And here you have, well, this very explicit formula, and then this new, that's how it relates to the parameters of your model. And for paramagnetic regime delta 1, you have to supplement this type of exponent also by extra exponential. And okay. Yes, and here you can basically plot. Right. Okay. Yeah. So and then so here's the answer for correlation length that comes from the imaginary part of this integral. Right, and then for in paramagnetic case, because you have this prefactor, there will be correction for your inverse correlation length. So it will be not only this integral, but plus something, which is like some constant that depends on magnetic field and anisotropy. But in fact, if you plot the inverse correlation length, so dots are just numerics, and then blue is just this formula with the integral, and red is just well, it goes like this. It's actually integral plus correction if h is bigger than 1. So even though, like mathematically, this formula looks like it's discontinuous, in fact, you need to have this correction to have continuous function. Otherwise, you would have some kind of phase transition, which was unthinkable at finite temperature. Well, and the same happens for the prefactor. So it's all finite, even though in h less than 1 and bigger than 1 formulas looks differently, but in fact they part of one continuous formula. And that's how this approximation works. So so dots are exact values, and blue is just basically this asymptotics.
So
and
m small was x. This is distance on the left,
sorry,
correct?
Sorry, yes.
M is x.
M is x. It's the distance between spins. So that's why it's in integers. And in normal cases, same as was for sine-kernel, usually asymptotics works almost at the beginning. So this particular case, we had to go to the ridiculously large anisotropies to see any difference. Otherwise, it's normally describes like this in generic cases. So that's just good to know. Okay, and just to compare our double integrals for the prefactor and the correlation length. So of course, all these quantities were computed a long time ago. However, they had very difficult expression, but so I think numerically we checked, and it's all the same. And in fact, those integrals they look formidable, but in fact, their convergence is pretty good.
You mean the same in the asymptotics, or
no? So this is answers for asymptotics. So for our asymptotics, we had some prefactor and correlation length, and this prefactor is just exponential of this double integral, and they have double product. And the reason was, yeah, maybe one can even prove that it's the same, but.
Well,
Okay.
you have proved that they're the same, right? Because they give the same correlation function, right?
Yeah,
the left-hand side from the very beginning was correlation function. You prove that's the same, right?
Yeah. But one can wonder because
direct proof. You mean direct proof? More.
Yeah.
Shortcut.
You can take log, then it will be double sum.
Yeah, right.
Then you can replace double sum by double integrals with some residues, and then maybe
of
you can
course.
just prove it.
I understand. Thank you for explanation.
Okay, so then
I can ask you something. So this means that you check numerically that the integrals, roughly speaking, equals the sums. Am I right?
Double products, yes.
Yeah, no, just numerically. Am I right?
Yes.
Thank you.
Yes. Yeah, because we still, why it's not rigorous, because we discarded this factors in the kernels, and we still don't know what is the error. So that's why it's not rigorous.
Yes.
Okay, so then in the end, I have like just two brief topics to cover, and one is to explain how the traditional approach for this problem, which was done in Topli's determinant, how it appears in our system. So it's very beautiful, and so first you just use some type of geometrical series to present the sine-kernel is just like sum of exponents. So it's not exact equality; it's some diagonal for factors, but they do not change integral. So it's just this. And then also it's suitable to just modify by introducing these factors a n of p. So normally for normal sine-kernel, all a n of p are just 1. Okay, and then basically you can consider your sine-kernel as a product of two matrices with two different type of indices. So one is just a momentum, and n is just this integer n that runs from 0 to x-1. Okay, and then basically how to go from Fredholm to Topli's, you just use this property. So you had a matrix that dependent on q and p. If you do BA, then you will have just on these integers and 0, and then your Fredholm will be just Topli's, so this is just the determinant n by n, where this Tn is just given. Okay, that's not exactly Topli's, sorry. It's well, it will be just discrete determinant that depends on n minus n and this factor. But when all a n are 1, yes, then you'll get literally Topli's. So that's the easiest way to get Topli's for Fredholm and back. Yeah, and then this function c, it's called symbol. It's related to this phase shift nu just by e to the 2 pi nu. Okay, but we did not really have literally this expression, so we had like difference of two Fredholms, and but this guy, this delta v, it was a finite rank. So in fact, all these expressions are linear in this delta nu. So if here will be some coefficient, it will just go outside. Therefore, this expression can be, well,
Alexander, it should come with different notations because the letter delta was equal to 0, 1 in the couple of previous transparencies. This is not the delta v. It's not the delta which was equal to 0, 1.
Right. So what to do?
Well, I don't know. By now it's probably okay, but for the next lectures, you know.
Yeah. Sorry. Yeah.
By now it's probably too much work to change last moment, but people should realize. Right. This is good. This is good.
Yes. Sorry about that. Right, and okay, so then we'll just consider this shifted determinant, and the reason why I introduced this an, it's actually that again we can present it in this form where a0 is shifted by alpha, just to account for the shifting of the finite rank, and the others are just 1. Okay. And then basically this determinant will be, well, it will be determinant of this type. So in first I will just I just shift by alpha, and because of this shift and because of this definition, it will be just alpha times sx. So Right. But then since we need only derivative at alpha to 0, then basically we can just neglect everything about alpha here, and then we can move this row to the last one, and it will just give us some factor and this determinant. So you see, contrary to the previous determinants, it starts not with 0 but with 1 and goes like this, and also it has some prefactor, but otherwise it will be some new matrix and C tilde. So we just prove this, where this C tilde is just, first of all, it gets overall sign because of this. And and shift in Q. But, and then we can call this new... Sorry?
Sorry for interruption. It's just noise, neglect.
Okay. Then this new one is just exactly this new with changed by the number. And then here it's kind of, even though I consider it like difference of two determinants, in fact, it's again just one determinant, but with this function with with a shifted phase shift. So I think it's and it's nice mathematical exercise. I don't know whether it's known or not, but yeah. And finally, all our asymptotics, they can be also reinterpreted in terms of sigma. So in the easiest case, when delta is 1 and you don't have any windings, then it's just this, where k are just Fourier modes of our nu, and then in particular this constant is just our beloved double integrals that we had in the asymptotics. So that's kind of nice relation to Joplitz and all this famous works done a long time ago. Right. Okay. So how much time do I have?
How much time do you need?
Well, I mean, okay, maybe 5 more minutes.
Oh, five minutes will be good.
Right. So then, as I promised, we also had some work for 5 minute time, and the main features that can be observed is that sometimes it's not enough just to have soft modes. Sometimes you might need the hard excitation, and it was called Luttinger. And then instead of like a typical behavior, you will have also 1 of square root t, which comes from the integration of these hard excitations. Okay, so that's how it does work for 0 temperature and the sine-kernel. So we have our old answer. This is just contribution of the soft modes, and then this impurity comes from, it differs whether it's within light corner or outside. So yeah, it's just gives a little bit different behavior, but again, if you check numerically,
so by now theta is Heaviside function, correct? This theta
yes.
Okay, thank you.
Right. Yeah, and then at least numerically, it seems that everything is working just fine. And yeah, okay. Right, but that's at zero temperature, so it's no big deal. It's probably even published by somebody. Now, at finite temperature, that's a little bit more complicated. And it turns out that, in fact, if you try to play the same game and get a continuous nu, you will not be able to do it like straightforwardly, because then this nu will have some explicit x and t dependence, and then at least the naive solution, it will be discontinuous, sorry. And so okay, that's very preliminary. So that we tried like different ways to regularize this function. Probably it's not really well, at least numerically it looks okay. So again, so black, yeah. So here we compare explicit expressions like red and blue and all is what is dotted is just asymptotics comes from our approach. It seems okay. Okay, exactly within light cone, it does not quite agree, but otherwise, it's pretty close. It's pretty close, but it's like work in progress. So yeah, hopefully I will be able to report on something this when I learn it properly. Okay, so with this, I would like to conclude. And again, just let me emphasize what was done. So we developed some trick. Probably it follows from the from factor summations by French group and from others. But what is doing effectively? It allows us not to solve Riemann-Hilbert problem to find asymptotics of Fredholm determinant, and we just take into account the state by the appropriate phase shift. So we can address it like according to our needs. Yeah, and then hopefully it's universal, at least in some sense. Then, as I mentioned, as for me, it's very interesting to apply this to get asymptotics of the classical integrable systems, what's called Markov ansatz, etc. I think here it should be very natural. And another interesting approach is that in different approaches to dealing a quantum system at finite temperatures, there's this quantum transfer matrix approach by Wuppertal group and others. And recently, like I think last year or 2019, they also applied it for XX, their technology, and somehow they will also came up with exactly identical phase dressing, but there they had some more rigorous approach. So yeah, it would be nice to make some connection, but it's still work in progress. So yeah, so with this, I would like to thank you very much.
Thank you. So let's unmute ourselves and thanks, Alexander.
Well, I can clap. You can clap with reactions. There is clapping in reactions, right? You can.
Yes, you can. But...
Can I make a comment on universality?
Yes, please.
So first, I like the lecture very much. This is beautiful. And speaking of universality, it's interesting that this approach, which Oleksandr explained to us, works not only for correlation function, but it also works for entanglement entropy. In XY model, I mean, the ground state is unique. So the entropy of the whole ground state is equal to 0. But if I consider a block of spin of some size, then there is entropy. And the approach to calculate this is based on Oleksandr formulas, Fredholm determinant, Riemann-Hilbert. So I send the link. That's the end of my comments on the universality.
Yeah, I can also comment on your work about the Sobolevic ladder, and indeed,
yeah. So
basically, it's very interesting because okay, so this is P. Rel about 93, I guess.
Reflectors, that's correct.
Yeah. So then the answer for tau function when there is time. So for
well, I mean, when there is time, you mean what we considered space-time and temperature-dependent correlation function. That's the way
exactly,
I pronunciate it. So that's my pronunciation.
So when t okay, so when you when t bigger than x, when you like in time like domain. So when then okay, then of course you have some x minus q. Okay.
With some integral, right.
Okay, I'll write in continuum. Okay, on lattice it will be something like this, like some sine q.
Well, for asymptotics, it doesn't really matter.
Yeah, then it will be this function mu of q. Of course, in your work it was somehow different. But what is amazing that instead of just a constant, there was some 1 over t to some power.
Yeah, correct.
X over t. So that's for me right now. It's like the most mysterious. How could it appear?
Riemann-Hilbert, you know.
Yeah, Riemann-Hilbert, but in this from factors. And I think like our working conjecture is that okay. So somehow these jumps in the effective nu of q are they real somehow. Then this integral, which we have all the time in the exponential, this double integral.
Yeah.
In fact, for continuous function, it diverges. So if for discontinuous function, but if you regularize it somehow with some function, so it just jumps with t, then it's exactly diverges as a jump of these guys exactly at x over t times, because you see it's 2 here and 2 here, so then it's will be some log t.
So then you might reproduce the power, right?
So hopefully, but it's like it would
well,
be
you know,
nice.
First I fully agree that will be nice to reproduce. I want to tell you that if in XX I consider time-independent correlation function, then asymptotics which come out, we have a naive hand-waving explanation. This is just from Jordan Wigner. But with time, we have to go through Riemann-Hilbert. But so if you will derive it and get some finite shortcut, simple physical meaning or simple derivation, that will have great value. So I will be very grateful.
Yeah. So it's so indeed for a static case, you can consider this correlation function as like a partition function with defined.
Exactly.
And that's kind of reproduce this formula, because each determinant it's like a partition function, if you wish, for free fermions, right? So then normally, if you derive it from Dirac lattice, then you will have this with finite rank. But then if you do a little bit of twisting, then you will have just one determinant as if it's partition function. And that's kind of should be the same that you did.
Well, good idea. I fully support. So thank you very much for your comments and for your replying to my comments. Okay, maybe somebody else has something else to say.
Okay, any other questions or comments?
So let's thank our organizer for organizing such a beautiful lecture.
Thanks.
So maybe I have a question, maybe not, I don't know. So if we go to the next order in one OL, let's say, this continuization conditions for K and Q, will it have some imaginary part proportional to one OL?
Yes, I guess so. But you see,
just a moment. If yes, then I have a question. So if yes, because you have differences in the numerator of K minus Q. If it is of order 1 over L, it means that you multiply by L. Yes, so this naively subleading guys goes in the leading term somehow.
Yes. That's exactly. Yes. No. But indeed, the step when you resum everything, it has to be done very carefully. So first you keep L up to the very last step. So this discreteness is super important, exactly because of of this divergences in the denominator. I know if I have. Sorry. Yeah. So indeed, you have to take into account all this quantization condition like pretty seriously. But once you then you do resummation, and then you present this guy as determinant as 1 plus 1 over L, and then something of Q and Q prime, and some 1 over L corrections, and something. If in principle, if you keep everything, but only in this point you can disregard, and then you will have like answer in thermodynamic limit. But that's probably technical answer. So naively, you could say why I can't just replace this summation over with integrals, like immediately will be some integrals. Well, exactly because of the singularities. Well, you cannot do it naively. Of course, there are some multiple integral presentations, but it's But coming to a question, like any regularization will be fine, whether it's complex or real. It doesn't. Okay. You wonder if K has imaginary part and then L goes to infinity, this guy might blow up or sometimes you have bound states. Yeah, and that would correspond to bound states. And okay, not in this particular situation. This particular situation, this imaginary part will be 1 over L squared. So, well, I mean, it will be well regulated 1 over L. But for instance, for some kind of impurity problems, then you can have like genuine bound states. Indeed, when K is negative, has some imaginary part, and then, yeah, well, there will be some zeros, etc. That will result in additional finite rank corrections. Yeah, that you have just to take explicitly. You have to take them out of the sum, and then, yes. If imaginary part starts to be order of 1, then you have to consider it like separately. And normally, it modifies kernels significantly.
So it means that if you want to think about next correction, so you should draw your contours, integration contours, such that I0, 0 from I0 is bigger than this 1 over L.
Yes. So normally, very good. Normally, indeed, these contours, it's like, so there are, okay, so there are Q, which are real, and K, which has some contour. And normally you take contour like this. So normally this size is not 1 over L, but 1 of the square root of L. So it will take everything order of 1 over L, but not more. Yes.
Yeah. Good. Okay. Any other questions? If not, let's thank Oleksandr again. And let's finish official part.